Good morning. Welcome to our presentation today on positive unintended consequences. How Campbell Lake Gravity Sewer Pipeline survived a magnitude 7.1 earthquake. My co-author is David Persinger from Anchorage Water and Wastewater, and he is Director of Operations and Maintenance. He is a past chair and director of the Alaska American Waterworks Association section. He's a member of the Water Environment Federation and a civil engineering graduate of the University of Alaska. I'm a 38-year veteran of the water industry and pipe manufacturing industry. I have presented here at ASCE Pipelines a number of times. I'm vice chairman of the American Waterworks Association A21 committee, which governs the standards related to ductile iron pipe, fittings, joints, linings, coatings, and installation. I'm chairman of the Alabama Iron and Steel Council and an Auburn University mechanical engineering graduate. Part of my career was spent covering the 11 states on the west coast of our country, including Alaska. At that time, I was stationed in Sacramento, and Alaska was part of my territory, and that's how I became involved in this project. And I have told countless people down through the years about this project and how unique it was. And when I learned that it had experienced this event, I was very eager to turn in an abstract and hopefully be able to present this project's story. When I got acquainted with David, who had not yet begun his career when this incident occurred in 1989, he thought it was great and was very helpful. And he and William O'Malley of Anchorage also have a presentation later today in Track A, dealing with how the project was completely restored after it was stabilized, which we'll hear about here in this presentation. Beautiful view of Lake Campbell. It's in Anchorage, Alaska, filled with lovely homes around the shoreline, beautiful docks, most of which have a seaplane attached to them. This is an aerial view. You can see the Campbell Creek lake bed underneath Campbell Lake. It's a 125-acre lake built in 1959 by a private developer. It was destroyed by an earlier earthquake in 1964, and the dam was rebuilt and, of course, continued to serve the community very well. And then on August 25th, 1989, a 100-year flood crested. Resultant damage to the Campbell Lake Dam called for it to be lowered to allow the dam to be repaired before it was frozen later that winter. Now, this and the next 8 slides are going to walk us through the sequence of this project. And it's important to note this because Anchorage Water and Wastewater and the Corps of Engineers cooperated with each other in a beautiful way to produce a resilient project economically, on time, and solve 2 problems at once. That same lowering of Campbell Lake would expose and allow access to significant areas of the lake bed for installation of the gravity sewer trunk line. The exposed areas of the lake bed would soon freeze thereafter. And while that lake bed area was frozen, the route of the trunk line would be trenched to a gravity flow grade. The bottom of the trench would extend to a depth as great as 22 feet below the lake bed. That's important because if this had not occurred, a force main would have had to be built instead of a gravity flow job, a gravity sewer project. And a force main would have been much more expensive to not only construct, but also to operate in the decades to come. So after the trench is dug to grade, the bottom of the trench would be backfilled with an aggregate base to further stabilize it and further guarantee the proper grade. And then unrestrained 48-inch diameter push-on joint ductile iron pipe wrapped in polyethylene encasement would be installed to grade for the gravity flow trunk line. That 48-inch diameter unrestrained push-on joint ductile iron pipe would be outfitted with concrete collars atop the pipe to resist buoyant forces. 48-inch diameter ductile iron pipe is going to have 507 pounds per foot of buoyant forces if the pipeline is empty. That's 10,000 pounds per 20-foot length of pipe. Significant buoyant forces inside a partially filled ductile iron pipe under the water. The unrestrained 48-inch diameter push-on joint ductile iron pipe would then be backfilled with aggregate to provide further stability and support in the lake bed soil conditions. And then finally, Campbell Lake would fill from the spring melt before the summer recreational season. The job bid on November 1st, 1989. I was there. I still have my notes from the bid. And it was a real trip down memory lane to dig those out of the file cabinet and be able to help prepare this paper. Beta Construction from Seattle was the low bidder at $3,716,000. The engineer's estimate was $4,900,000. The high bid was $5,434,000. So the engineer was about in the middle of the pack, which is probably where he wants to be. Fast forward 29 years to November 30th, 2018. A magnitude 7.1 earthquake struck the area. The pipeline laid to grade with concrete collars atop it inside an aggregate-filled trench was disturbed. The concrete collars were shaken off, and the buoyant forces pulled the pipeline up. The greatest deflected joint was deflected 14 degrees. It was also 14 feet above its original grade position, and a 16-inch thick ice layer held it in place undetected. The force main, the gravity sewer line continued to operate, obviously being completely filled upstream and then spilling over that elevated joint. So fast forward 104 days later to March 14th, the ice had melted enough that the buoyant forces allowed the pipeline to push through the ice like a surfacing submarine. And boy, did that get some folks' attention, and they started scrambling. They quickly put together this strong back assembly, drove it into the lake bed to stabilize the pipe, to hold the joints together so they wouldn't separate when the ice was completely melted. And then they developed plans to further restore the project. And again, that's a presentation by William O'Malley at 12:30 in Track A later today, and I invite you to join in for that. Okay, the most deflected joint, 14 degrees. These joints have a 9-inch socket depth. About 6 inches of that spigot is exposed here in this grossly deflected view. You see the loose polyethylene encasement that was pulled back to expose this joint. You see the excellent condition of the pipe surface. This is the American Fast Tight joint in straight alignment. It's the joint that was used for this project. The other brand of push-on joints for ductile iron pipe is called Titan. They both use a dual durometer gasket. In the Fast Tight brand, that left-hand portion of the gasket is the higher durometer. It's inside a square socket groove that holds the gasket in place, and the wider part to the right, which is thicker and fatter, is the softer durometer, and that's where the bottle-tight, watertight joint is made. The gasket groove is cleaned. The gasket is placed inside the gasket groove. The gasket is lubricated. The spigot is lubricated, and then the same backhoe that dug the trench is typically used to push the spigot inside the bell. This is a cross-section drawing of the same joint in straight alignment, showing the dimensions, in particular the 9-inch socket depth, the 50.8-inch outside diameter. This is the special deflection fast tight joint. The regular deflection fast tight joint in 48-inch allows 3 degrees design deflection, 12 inches offset. Because this project is remote, because it would take an awfully long time to ship any specially made joints to the job site, special deflection bells were machined, providing an extra degree of deflection. an additional 5 inches of vertical offset for each 20-foot length of pipe. And this is a engineer's drawing of the 4-degree design deflection. This is the 14 degrees as deflected after the earthquake. This reminds me of what an X-ray of an almost broken leg might look like. It can be quite stunning when you first see this and see how much of the spigot has pulled out, and yet the gasket continued to stay in place. The spigot did not fully separate. The joint continued to perform and did not leak. This is a side-by-side view showing the 4-degree special deflection bell on the top left and the 14-degree as experienced deflection on the right. A dramatic comparison of resilience of performance outside of design conditions. So let's look here at a little project history. It's 3,337 miles from Birmingham, Alabama, where this pipe was manufactured, to Anchorage, Alaska. The project, the pipe would move by piggyback trailers loaded on rail cars from Birmingham to Vancouver. Those piggyback trailers would then be transloaded to barges and moved up the Alaska inland passage to Anchorage. And those piggyback trailers would then be offloaded from the barges and trucked to the job site at Campbell Lake. The first shipment was made December 14th, 1989. The freight cost for the piggyback barge truck combination was a total of $185 per ton. That's $609 per 20-foot length of pipe. That's $30.45 per foot. The delivered pipe price was $110 per foot. So freight was 28% of that total delivered cost. And at $110 a foot for the 8,432 foot long project, the pipe material cost $927,520, and that's 25% of the $3,716,000 construction cost. Quite a bargain, if I may say so. And again, you will later today in track E, you'll see another paper called What is Pipeline Resilience? And I would invite you to tune in for that. A number of experts were interviewed for that paper, one of whom is Charles Anderson, former AWWA president, and working with CDM Smith in Fort Worth. He says that joint performance is a component of pipeline resilience. John Platzmeyer, retired from HDR, a frequent presenter at this conference and well known to many in this audience, says that pipeline resilience includes the ability to recover. So I would invite your attention to that paper as well. Another component of pipeline resilience from the experts interviewed for that paper includes the topic of sustained performance. Now, after 29 years in lake bed sediment, with the use of an annealing scale and asphaltic top coat and double wrapped in traditional polyethylene encasement, there were excellent results with respect to corrosion and sustained performance in that regard. You see the detail of the peen pattern on ductile iron pipe in this photograph of the 14-degree deflected joint. So what if this project were designed today? How might it be designed differently? What advancements have occurred in ductile iron pipe technology that might be employed today? I would expect the flex ring joint would be used instead of the unrestrained fast tight joint. That would include the same fast tight gasket with dual durometer and bottle tight sealing. It would include a restraining well bead on the spigot that would engage with a rubber back assembly with locking segments to prevent joint separation, and it would still allow joint flexibility. This is a remarkable combination of joint performance. An even more remarkable combination of joint performance are seismic joints. This particular design includes 8 degrees deflection, 3 degrees on the left-hand side of that red casting, and 5 degrees on the right-hand side of that red casting. It includes tremendous end-wise thrust resistance and thrust capacity, yet it also includes longitudinal expansion and contraction, 2.4 inches each expansion or contraction, for a total range of motion of 4.8 inches if you go all one way instead of splitting the difference. I would expect if it were designed today, it would also include zinc coating, and it would probably also include VBIO enhanced polyethylene encasement instead of traditional polyethylene encasement, which was the only thing available at the time this project was constructed. Now, I have recently completed a presentation to the NACE Corrosion Conference that studied a zinc-coated VBIO encased polyethylene encasement study in the Everglades, and the samples were monitored even after intentional damage to the wrap and the coating, and the extrapolated expected life using those corrosion probes for those samples in North America's most corrosive environment was 1,666 years. Now, Greg Horn of the Ductile Iron Pipe Research Association, who just dialed my phone a moment ago, and you may have heard it ring, by the way, is presenting later in this conference on the 60-year history of traditional polyethylene encasement. Now, the difference in VBIO and traditional encasement is that VBIO includes an antimicrobial compound to kill bacteria and germs on the surface of the pipe that can result in some corrosion. It also includes a volatile corrosion inhibitor infused into the inner layer of the pipe, and we changed the color from black to white. So if you want to see how this project was reconstructed, I know they reused the pipe. They took some apart and replaced the gaskets, all wise measures, and rebuilt this very soon thereafter. A fascinating presentation by William O'Malley of the Anchorage Water and Wastewater later today at 12:30 in Track A. Now, if you read the written version of this paper, the concluding statement is, the use of ductile iron pipe with its push-on joints and rubber gaskets allowing liberal deflection and its encasement in protective polyethylene 29 years before a potentially catastrophic seismic event made possible survivability and restoration of a critical infrastructure in an environmentally and economically sensitive area. Truly pipeline resilience. So thanks very much, and I'd be happy to take your questions.